Welcome to aminacademy.com. In physics, let us discuss about stress strain curve. A stress strain curve is defines how a material behaves under load, which provides insight into the material's strength, stiffness, ductility, and failure limits. For example, a glass marble dropped to the ground would shatter immediately into more pieces, while a rubber ball would return to its original shape after the impact. What's the difference between here glass and rubber? This difference in material behavior between a glass marble and a rubber ball can be completely explained by stress strain curve. The relationship between the stress and the strain for a given material under tensile stress can be found experimentally. In a standard test of tensile properties, the test cylinder or a wire is stretched by an applied force. The fractional change in length, that is the strain, and the applied force needed to cause the strain are recorded. The applied force is gradually increased in steps and the change of the length is noted. A graph is plotted between the stress, which is equal to the magnitude of the applied force per unit area, and strain is in other axis. A typical graph is drawn like here. We'll explain what is the features in this graph. In a region, the point A to B, stress and strain are not proportional. Here, from 0 to A, the stress and strain is proportional. That means it obeys Hooke's law for some set of loads. After increasing the load, the point A and B is not exactly straight. Nevertheless, the body still returns to its original dimensions when the load is removed somewhat. The point B in the curve is known as yield point. Point B is the yield point because after this point it won't obey the Hooke's law. Here point A to B somewhat it will obey. The point B is the curve is known as yield point, also known as the elastic limit. The corresponding stress is known as yield strength of the material. If the load is increased further, what happened? The stress developed exceeds the yield strength and strain strength. Strain increases rapidly even for a small change in the stress. The portion of the curve between B and D shows this. Here B and D is this here. Exactly, some more changes in cross-sectional of the wire is happening here. If the load is increased further, the stress developed exceeds the yield strength and strain increases rapidly even for a small changes of the stress. The portion of the curve between B and D it shows. When the load is removed, say at the point C, between point C and B and D, the body does not regain its original shape. After removing the load, the stretched body will not come to its original shape. In this case, even when the stress is zero, the strain is not zero. The material is said to have a permanent deformation. After this, beyond this point, the material is in deformed position. The point D on the graph is the ultimate tensile strength. At this point, the ultimate tensile strength is happening, that is sigma u of the material. Beyond this point, additional strain is produced even by a reduced applied force and fracture occurs. The fracture occurs at the point E. If the ultimate strength and fracture point D and E are close, the material is said to be brittle. If they are far apart, the material is said to be ductile. These are some points on this stress strain curve. Next, we'll discuss about strain energy. Here, the elastic potential energy gained by a wire during an elongation with the tensile strength or compressive contractile force is called strain energy. That means some energy stored while compressed or elongated in the material is called a strain energy stored. For linearly elastic materials, strain energy is here sigma is stress, Young's modulus is strain, and V is volume, and E is Young's modulus. Look at here. Here work done equal to half F A F delta L, half into force into distance. That is a strain energy stored here. Here this is under Hooke's law. Here it is not obeys Hooke's law, non-Hooke's law. The work done is area under the curve. Here actually this also area under the curve, but it is exactly triangle, so it is half force into delta L. Here by using integration you have to calculate work done, that is area under the graph. The strain energy is a sort of potential energy. It is stored in a structural part due to elastic deformation. For example, a bar is said to be deformed from its unstressed state when it is bent by applying force on it, and the amount of strain energy stored in is equal to the work done on the bar by the force. Only its stress is below the elastic limit can the strain energy stored in the material be translated into kinetic energy. Plastic deformation happens in the material when the stress need exceeds the elastic limit. The sum of the energy is wasted in this process. An object made of deformable material will change shape when a force is applied on it, like rubber. The object will continue to stretch as we apply a greater force. The amount of force applied divided by the object's cross-sectional area equals stresses as equal stresses. Now we'll do some further explanation of strain energy stored. Here we'll calculate work done in strain energy stored by this method. Look at here. Work done equal integral 0 to L Y A L. Young's modulus, cross section area, and length. This is delta L. Delta L by L dl. Now this we put this model here. Okay, then it is equal Y A Y by 2 and L squared by L after integrating. Now which is equal half into Young's modulus into strain square. strain squared into volume of material, volume of the wire material. So this is, we can write, that is strain energy stored. You can write this as half sigma with elongation. Some application of the elastic behavior of materials. The elastic behavior of materials plays an important role in everyday life. All engineering designs require a precise knowledge for the elastic behavior of material. For example, while designing a building, the structural design of the columns, beams, and supports require knowledge of strengths of materials used. Now, further detail, we'll do some example problem in next video. So far we have done strain energy and stress strain curve for some materials. We have done. Please subscribe our YouTube channel.